Okay, so everything we've done with this graphing and solving equations has been to build up to what we're going to cover in the next couple days. And what we're going to be covering is systems of equations. Now, a little bit of a review to build up to that. If I have y equals 2/3 x minus 1, if I go to graph that equation, where do I start? -1. And from there I go up to over 3. There's my line. What does that line represent? Well, it represents an intercept and a slope, but to this equation, it represents every set of solutions. Every point, a pair of points, it's a solution. For example, right here, this is it. X equals 2, y equals 2/3. That's a solution. Or sorry, actually, x equals 2, y would equal 1/3, but you get the point. That is a solution to that equation. Every point on that line, if I find its x coordinate and its y coordinate, I can put the value in for x and the value in for y, and it'll make that equation true. So let's say I have another equation. Y equals a negative 2x plus 7. Where's that one start? 1, 2, 3, 4, 5, 6, 7. Right there. From there, where does it go? Down 2 over 1. And I'm just going to keep going. Down 2 over 1. Down 2 over 1. There's my line. What does that green line represent? All of the points that are solutions to that green equation. Every point on that line, if I pick that point and find its x coordinate and its y coordinate, put them in for x and y, that'll make that equation true. Does that make sense? Yeah. So when I give you a system of equations, what I'm doing is I'm going to give you two equations, and I'm going to ask you, give me the values for x and y that make both equations true at the same time. Well, on the graph, where would that be? That would be where the two equations cross, right? Right there. That's the only point that makes both equations true, because it's the only point that's on both lines, where the two lines intersect. That coordinate is 1, 2, 3, 1. So the point 3, 1, the ordered pair 3, 1, is a solution to both equations. Therefore, it is a solution to the system. Now, since these are linear equations, they make lines, they can only cross once. So there's only two options. Well, there is three options, I should say. The first option is what we just have. They cross at a single point, and that single point is the solution to the system. The second option, of course, is the two lines are parallel, and then, of course, there's no solution. The third option is that one of the lines lies on top of the other. In other words, the two of them are the same line. And then everything that's a solution to one equation is a solution to the other equation. So, no, it's not infinity. Infinity is not necessarily a solution. It's just, what you usually do is just write down one of the equations for one of the lines, because whatever's a solution to that equation is also a solution to the other. But it doesn't mean any, and a lot of people write down any number. No, that's not true. You can't take any pair of numbers. They have to be numbers that are on one of the lines. Some people say there's infinitely many solutions, which is true, because there are infinitely many, but the solution is not infinity. There's a slight distinction there, an important distinction there. So in your notes, I want you to try to graph these two equations and see if you can figure out where they cross. 6-1. Okay, let's take a look. This equation here, where do we start? Okay, up 3. Oh, sorry, I'm fighting off a sneeze here. Say at 3, then from there we go down 1 over 3. And I'm going to do it again. Down 1 over 3. Second one, where do we start? negative 2, and from there we go up 1 over 2, and I'm going to do it again, up 1 over 2, and one more time, up 1 over 2. There we go. And they do cross right there at 6, 1. How many of you had 6, 1? How many have no clue how we got 6, 1? You doing okay?
Yeah, I got close.
Just a little off on your graph. Notice how I did the slope once and I just keep going a ways. That way I have exact points where the slopes work out. Now, I do it, the examples I give, I do it so they come out on those points. In the book, they sometimes don't. In the book, there actually are a couple that come out to be like fractions or decimals. I don't expect you to be able to get fraction or decimal answers. Anything I give you on a quiz or a test, if I want you to solve it by graphing, it will be an integer value. There's not going to be a fraction or decimal on it. Because graphing is not meant to be that accurate unless you're using a CAD system or some sort of electronic graphing system to do it. Then the computer can give you that exact decimal. But in real life, yeah, even there it's sometimes touchy if it's a tight decimal getting your trace function to do it. There's a solver function on there though that'll find it a little more exact. But yeah, it's not. Graphing's not meant to get exact decimal or fraction answers. But our equations won't always be quite as neat as those ones that I just gave you. We might have this. Oh, let me make this work a little better. Try to graph. It's going to be the exact same equation, isn't it? Never mind. I'll make this work out a little bit better for you. What's that? Yeah, that came out to be the exact same equation. That's not going to work real well. Try to graph those, see what you come up with. You'll notice that first one, you got to solve it for x before you can graph it. Okay, now, so this first one here, we're going to have to subtract 3x. So I got negative 2y equals 4 minus 3x. And then divide by negative 2. So y equals negative 2 plus 3 halves x. So I start at negative 2 and I go up 1, 2, 3 over 2 right there. Like that. This one, where do I start? It's kind of confusing because there's no plus or minus, but that means I start at 0. And from there I go up 1 over 2 right there. So my solution is 2, 1. What do you think? Tomorrow. On page 409, exercise 17-1, there's 1 through 17 if you want to work on the odds. What's that?